Yes, thank you very much. Yes, so for those of you who don't know me, I'm Adam Boland. I'm a postdoc at Berkeley, and today I'll be talking about joint work with Shalef Ben-David, Ankit Garg, and Robin Kothari, the latter two of whom are in the audience now. So when you think about quantum computing, and when you come to a quantum computing session at Fox, you normally think that you're going to hear something about building and understanding the computational power of quantum computers. But the thing is that actually quantum ideas can sometimes be useful for other things too. For instance, they can sometimes be useful to study classical computation as well. It turns out that oftentimes one can prove statements about classical computer science using quantum ideas and techniques, even though the result has nothing to do with quantum mechanics. And this has been dubbed the quantum method in analogy to the probabilistic method of combinatorics. And if you'd like to read up on some examples of this, there's a nice survey of this by Drucker and DeWolf. For instance, a famous example of this is the non-existence of two locally decodable codes was first shown using quantum techniques. So today I'm going to be talking about just exactly such a result. I'm going to talk about a result which uses quantum techniques to prove some new facts about something called the approximate degree of Boolean functions and some related notions in communication complexity. In particular, our main result is going to be a lower bound on the approximate degree of certain compositions of functions and some related quantities in communication complexity. And our proof will make use of a quantum algorithm of Belov's. And thus far, we don't know of any classical proof for this statement. So you can kind of see our results as combining the quantum method with what Scott Aaronson has dubbed ironic complexity, that is, using upper bounds to prove lower bounds. All right, so let me explain a little more in detail what our result is. So if you have a Boolean function f, the approximate degree of f, which we denote by deg-twiddle of f, is a certain classical measure of the complexity of f, in quotes, which was defined by Nissan and Szegedy in '94, though ideas of using polynomials in this thing are much older. And it's defined to be a minimum degree of a real polynomial p in the variables x1 to xm, one for each bit of the input, such that that polynomial approximates the function f, say to some constant amount of error. I mean, literally, if you plug in the value x into the polynomial, it will evaluate to something either close to 0 or close to 1. And the approximate degree of Boolean function has played an important role in quantum complexity theory because by a classic result of Beals et al., it lowers bounds the quantum query complexity of the function f. That is, how many queries do you have to make to the inputs to the function in superposition in order to compute it with bounded error on the quantum computer. So in this talk, I'm going to be trying to address a fundamental problem of approximate degree, which is how does it behave under composition? So what do I mean by that? Well, let's say now we have two Boolean functions, f and g, on n and m bits respectively. Then you can define the composition of f with g to be the function where you take each input to f and you replace it with a fresh copy of g on a separate set of input bits. So if you were to represent this pictorially, you see on each input to f, we've replaced it with a copy of g acting on its own set of inputs. And the question we're going to be trying to address in this talk is what is the approximate degree of f compose g in terms of the approximate degrees of the original functions. So prior work has shown that the approximate degree of f compose g is at most the product of their approximate degrees up to constants. And this is a result of Shorstov from 2012, which improved on earlier work of Berman et al.
Are you missing a twiddle here?
No, I'm not missing a twiddle here. Yes, that was the improvement between Shorstov and Berman. Yes. And the proof is essentially just to compose the polynomials. The basic idea is you take if you have your polynomial for g, you just compose it into your polynomial for f. That multiplies the degrees. And that this proof essentially works with some log factor fudges. But this is essentially the proof. But this leaves open, is this construction optimal? Is it true that the approximate degree of f composed g is at least the product of their original approximate degrees as well? Yes? Oh, yes. I forgot the twiddles, yes, because I did some of this in PowerPoint and not in Beamer, yes. Oh, sorry, yes. So I mean the twiddles. Yes. Yeah, good. Okay, so I just pretend there are twiddles everywhere. Okay, good. All right, and now it's much more difficult to prove the lower bound on the approximate degree because, here you're trying to show there's no better polynomial that exists other than the ones from composing the optimal polynomial for each. So, it's always harder to prove a lower bound than to prove an upper bound. So as a result, this lower bound was only known for special cases of f and g. So for example, one famous result in this direction is what's the approximate degree of something called the and/or tree? This is just you take the or of n ands of n variables. And there was a long sequence of works which eventually proved the corresponding lower bound, that the approximate degree of the and/or tree is at least the product of its approximate degrees as well. And there were a series of papers over almost 20 years in order to resolve it for this series of functions. And it was finally resolved in 2013 by Scherstov and Bunn and Thaler independently. A second related prior result is a result of Scherstov, which shows that the approximate degree, again, there are twiddles here, of f composed g is at least, deg f squared over n times the approximate degree of g. So this gives you the optimal lower bound when the approximate degree of f is linear. So for instance, if f is the parity function, then we know an XOR lemma for approximate degree. And our result is going to be to try to generalize this previous results on the and/or tree. We're going to show that for any function f, the approximate degree of the or of n copies of f goes up by at least a factor of square root n. And square root n is the approximate degree of the or function, so this is optimal. And we'll furthermore extend this to all symmetric functions s, up to log factors. So here when I say a symmetric function s, I mean a function that depends only on the Hamming weight of its inputs, analogous to the OR function, the majority function, the parity function, etc. So if you compare our results to what was previously known for the and/or tree, what you can see is that we've generalized this result towards a more general composition theorem, and furthermore, we've achieved it with a completely different proof technique. We also extend these results on approximate degree to communication complexity. So in quantum communication complexity, there's a quantity called the log approximate gamma 2 norm, which lower bounds the quantum communication complexity of a function with an unlimited amount of pre-shared entanglement. And we showed that this quantity obeys a similar scaling up when you compose with the OR function and with symmetric functions as well. In the communication realm, we end up losing some more factors, like we lose a log on the first one and we lose a little more than a log on the second one. But these are essentially optimal composition results for the log gamma 2 norm, approx gamma 2 norm of these communication problems. And using this OR composition for quantum communication, we can reprove some powerful old results. So, for instance, one of the most favorite problems in communication complexity is the disjointness function. That is, you're given two sets as inputs, and the parties want to determine if their sets are disjoint. Well, you can think of this as the OR of a bunch of ands of a much simpler function, which is just, do the sets intersect on one particular element of the universe? So using our result, this immediately gives you as a corollary that the log gamma 2 norm of disjointness is at least square root n. In fact, we can shave the logs off in this special case. So this reproves Rasborov's celebrated result of lower bound on the quantum communication complexity of disjointness. We can even use our techniques to reprove Braverman et al.'s more recent result on something called the quantum information complexity of disjointness as well, which is similar to quantum communication complexity, but instead of charging for communication, you charge for the amount of information in the messages between the players. So to summarize, in this work, we've characterized how approximate degree and some related quantities in quantum communication complexity compose under symmetric function composition, at least up to some logs and some small factors. And these results both generalize previous results, say on the and/or tree, and can be used to reprove some known communication lower bounds. All right, so how do we achieve these results? Actually, all of these results have a common technique. In particular, they use a very clever quantum algorithm of Belov's for a seemingly unrelated problem called the combinatorial group testing problem. And if you indulge me for a moment, I'll describe to you what this problem is. It won't seem like it has anything to do with our original problem, and then I'll bring it back and explain why this actually proves an OR composition theorem. All right, so combinatorial group testing actually has a kind of fun and interesting history. Its origins are historically from the World War II testing of US Army draftees for syphilis. And at that point, the Army was trying to achieve the following goal. They took blood samples from each of the N draftees, and they wanted to determine which of these people had the disease. And they had access to a blood test which detected whether the antigen was present in people's blood for the disease. And the insight of combinatorial group testing was that if you take multiple people's blood samples and mix them together, you can learn whether anyone in the group had the disease or not. And using this, you might be able to, say, save on the number of tests you use. So to see how this works, if very few people have the disease, it's very easy to see that you can use fewer than n tests. So for instance, suppose that you had a pool of n people and you knew exactly one person had the disease. Well, you could just pool the blood samples into two equally sized groups and then test those groups together. And you could learn that, say, one group has someone positive in it and the other group does not. And from this, you could recurse and do a binary search. In fact, you can easily see that if you knew that k people have the disease, then you can get away with using only k log n tests instead of n, by simply repeating k binary searches. Now, while this result is very useful in practice, because this is actually, in the real world, you have sparse input vectors to this, for worst case inputs, you still need at least n tests. It's very easy to see this because the problem reduces to search if everyone has the disease except one person. Because then, the only group that will test negative is just the singleton of the non-sick individual. All right, so I'm now going to just restate this problem much more formally. So formally, we have some hidden string x. This is the list of the disease statuses of the individuals. And our goal of this problem is to learn x. And the queries we're allowed to make is we're allowed to specify a subset S of individuals, and you can learn the OR of their disease statuses. So that is, we have access to these Boolean variables x of S, one for each subset. So now there are 2 to the n different variables. And our goal is to learn x, promise that these variables all come from some hidden string x in this way. And the classical complexity of this is theta of n for this query problem. All right. So since you're in a quantum session, you know what's coming next. We're going to say, now, what if we make a quantum generalization of this, where instead of just making these OR queries of subsets, what if we could make them in superposition? And this was first studied by Ambinus and Montanaro. And of course, the connection to blood testing is starting to break down because we can't test people's blood samples in superposition. But you can define this problem formally, nevertheless. And surprisingly, in 2013, Belov showed that the quantum query complexity of this learning problem is only square root of n, even for worst-case inputs x. This is maybe somewhat surprising that you can perform this learning task this efficiently. His proof of this result uses something called the quantum adversary method, non-negative weights, which I don't have time to explain, but it's a really beautiful proof. His proof fits onto a single page of text and involves the number pi. So it's kind of a magical proof. None of us really understand how Belovs came up with this. And it's not particularly constructive. It just tells you that this quantum algorithm exists. But nevertheless, it's a very beautiful result. All right, so thanks for indulging me on that combinatorial group testing detour. I'm now going to explain why this actually helps you prove composition theorems for approximate degree. And I'm just going to show it for the OR function, because this is the simplest example. And I'll discuss how it gets generalized soon. All right, so recall our goal is to lower bound the approximate degree of the OR of n copies of f. So the way we're going to do this is say, okay, so let's suppose that the approximate degree of this function is some quantity t, where t is something kind of too small. The basic idea is we're going to take the polynomial which exhibits this, this low degree polynomial for the OR, and we're going to compose it with Belov's algorithm, and Belov's algorithm gives rise to a polynomial by Beals et al. And we're going to use it to get a too good to be true polynomial for a much harder problem, for which we have an existing lower bound. All right, so to see how this works, so if you think about the polynomial arising from Belov's algorithm Q, what is it expecting as inputs? Well, it takes as inputs ORs of subsets of bits, right? That's what the combinatorial group testing takes as inputs. And its degree or its cost is square root n. Now, if we have some polynomial p for the approximate degree of the OR of n copies of f, well, this kind of looks like what the input to Belov's algorithm. Because, if you think of your, if you have the OR of n copies of f, there's some hidden string here, which is what's the value of f on each of the separate copies of variables. Then if you fix, say, some of the inputs to be 0, you can turn this into a polynomial for each subset of bits, which for each subset of this hidden string, which represents the OR of the bits in that subset. So now these things look like they just plug together. So we just do that. And what you end up getting is you get a polynomial of degree t times square root n, which computes the values of this whole string of f's. So in particular, you could say compute the parity of the bits of the string. But as I mentioned before, by Shorstav's prior work, we already know an XOR lemma for approximate degree, so we know that thing has to have at most degree n times approximate degree of f. And just dividing each side by square root n gives you the result, that the degree of OR of n copies of f has to be at least our claimed bound. So to summarize, if there were a better polynomial for the approximate degree of OR of n copies of f, then if you combined it with Belov's algorithm, it would give you a too good to be true polynomial for the approximate degree of the XOR of n copies of f. And for this, we already know a lower bound. Of course, the proof of this is not actually that simple. So what's under the rug here? Well, if you look at these plugs, as many of you might have experienced here in Paris, they don't actually fit together. And that's true here too, actually, because Belov's algorithm expects Boolean inputs, and our approximate degree polynomial p has non-Boolean outputs. But fortunately, there's an off-the-shelf adapter you can just go on the street and buy that that solves this. In this case, Scherstav's result has a very generic result that shows you can make polynomials robust to receiving approximately Boolean inputs. So we just use that. Yeah. Oh yes, that's right. Yeah, so this might be okay. So for the symmetric functions, passively a different adapter is needed, or some more chain of adapters. That's actually what happens when we generalize to symmetric functions. We have to open up the black boxes of the Scherstav robustification and the Belov's algorithm as well. So I'll refer you to the paper for details. But it's the same basic idea of using this two kind of very good polynomial Belovs to derive the lower bound. All right, I think my time's up, so I'll conclude with a few open problems. I guess the main open problem is to extend this to a general composition theorem lower bound. This we still don't know how to do. It's not clear our techniques will actually help here. A question that a number of classical complexity theorists have asked us is, can you make a classical proof of the statement that doesn't use Belov's algorithm? So usually the way you prove lower bounds of approximate degree is using something called a dual witness or a dual polynomial, which is you can write approximate degree as a linear program. So a dual solution is a certificate of a lower bound of the value of the program. This we still don't know how to do. And maybe the final more open one is, Belov showed that if you have OR queries to subsets of bits, you can learn a string very efficiently. What if you had F queries for a different function F could you possibly learn the string X more efficiently? And this is kind of a very open idea, but maybe this could help make progress towards the more general bound. All right, thank you for your attention.